Good afternoon, guys. Can you hear my voice?
Good afternoon, sir. Yes, sir.
Okay. Uh, Let us wait for 1 or 2 minutes. We'll start the class. Okay, let me share my screen so that we can start the class. Is my screen visible?
Yes, sir.
Okay, let me revise what we discussed in the previous class so that today's class discussion also will be in continuous to the previous class. We started discussing virtual memory management. We tried to understand that even though your memory, uh, I mean the file size or the process which is bigger than the actual memory, still you'll be able to execute that because of the virtual memory. And what is the main issue here is like uh, page replacement algorithms. Like whenever you are making bringing a page, you need to replace it with the new pages, and there are many replacement algorithms. We tried to study in the previous class FIFO, for first in first out page replacement algorithms. This is the simplest algorithm where it is carrying the idea of first in first out like a simple queue. And for this example, we try to understand if these are the pages and you have this frame, whenever you are bringing this page into a frame, that we will consider that as one page fault. And we try to observe with this example, for example 7 you are bringing to the frame, and 0 is bringing to the frame, and 1 you are bringing to the frame. So this will take 3 page faults, and whenever you are bringing to the oldest page that you brought is 7. So we try to understand using a uh, simple queue mechanism. So you will insert at the rear and you will delete at the front. So whenever you are deleting, uh, initially front and rear will be here. So you will keep inserting front. Front will be here only. Rear will move. Rear will move ahead, but front will be here only. It's like a circular queue. Then again front will be here, then rear will move, and we will keep inserting. After this you have to delete the element which is the front, and you will insert the element at the fourth. So front is pointing at the 7. So next, when new element is coming, new page is coming, 2 is not in this frame, so you have to bring this page into the frame. Now you will replace with wherever the front is pointing out, so it will be replacing 7 by 2. So 2 will be replacing 7. Front will now move to the second position. The second oldest element will be now pointing at the second position. Next element is 0, but 0 is already in the frame. We will no need to replace it. Next element 3 will come. 3 is not in the frame, so we will bring 3 into the frame. So now 0 will be replaced by 3. So after 0 replaced by 3, front will go to the next position. Next element what will bring is 0. 0 again there is not in the frame, so we will replace this 1 by 0, and front will move now to the next element, that is the next oldest element is this guy, 2. Now next, when 4 is coming, 4 is not in the frame, so 2 will be replaced by 4. So 2 will be replaced by 4. Front will move to the next position. It will point to this value. Now 2 is coming, 2 is not in the frame, so 3 will be replacing 2. uh, so front will again move to the next position. uh, Next 3 will come, 3 is not in the frame, so 0 will be replaced by 3. Then front will go to the next position. Once 3 is replaced, next element is coming 0. 0 is not in the frame, and we will this page we will bring into the frame. So 4 will be replaced by 0. Front will move to the next position, it will point here only. 3 will come, 3 is already there in the frame, no need of page fault, no need of replacement, so there will be no page fault. 2 will come, 2 is also already in the frame, there is no need of replacement. 1 will come, when 1 is coming, it is not in the frame, so 2 will be replaced by 1. Next friend will move to the next position, but you can observe that 2 will be replacing 1. Next element 2 is coming, 2 is not in the frame, so 3 will be replacing 2. So next friend will go to the top position, but 3 will be replacing 2. Next element 0 is coming, already in the frame, no need of replacement. 1 is coming, and no need of replacement. 7 is coming, so 0 will be replaced by 7. Friend will move to the next position. So next element 0 will come, 0 is not in the frame, 0 will be replacing 1. After replacing, friend will go to the next position, 1 will come and 1 will be replacing 2. So when next frame comes, then friend will point at the top. So whenever the next element, next page is coming, it will be replacing the top element. So for this reference string, we observe that we have 15 times we have to update the frames with the pages. So whenever we are bringing a new page into the frame, we call that as a page fault. So you can count that there are total 15 frames, 1 2 3. So total 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So you can see that 15 times the page frames were updated, which will cause 15 page faults. But FIFO is a bad replacement algorithm, because assuming this string and we carried out with 1 frame, 2 frame, and 3 frame, when the number of frames increasing, ideally the number of page faults should decrease. But sometimes you can see this, it is decreasing but again increasing. So for some page replacement algorithms, when the page fault increases as the number of frame increases, this we call that as a Belady's anomaly, which will be exhibited by mostly FIFO algorithm. So although FIFO page replacement is very easy to understand and program, its performance is not always good. We'll never know that the Belady's anomaly will come, and the number of page faults may increase instead of decreasing. So these are the things that we discussed in the previous class. Now let us continue our discussion on continuation of this virtual page replacement algorithms today also. This will be your 25 part 2, right? This will be part 2 lecture 25. Okay, so let us now start part 2. So we studied the FIFO page replacement algorithm, and let us now continue our discussion on remaining algorithms. So let us now discuss the optimal page replacement algorithm. But before that, would you like to ask any questions so far based on this discussion that we had so far? If you have any doubts or questions, you can ask.
Sir, does every system has a virtual memory?
Yes.
Like, sir, when we buy a pen drive of 4 GB, then some of the space is not available. Then that space is used for virtual memory, or
See,
it is something else.
virtual memory is like, see, your RAM is consists of 4 GB. Okay,
Okay.
if your file size is 8 GB, what happens is that 8 GB file will not completely brought into the RAM. Some part of that only will be brought into the RAM, and rest of the part will be storing in your hard disk only. Okay,
Okay.
you understand the concept of virtual memory. So in main memory, whenever a process need to execute, it should be brought into the main memory, correct?
Yes, sir.
Ideally what will happen, you will bring the entire process into the main memory to execute it.
Yes, sir.
But in virtual memory, if the file size is more, how you will fit into the main memory? It won't possible, right?
Yes, sir.
Suppose if your RAM is 4 GB and you want to play 8 GB movie, it's not possible. You cannot bring the entire file into the main memory. Now, what happens is the operating system handles in a such a way that only some part of the program will be brought into the main memory. It will execute it. After executing, it will finish. Then another part will bring into the main memory. For example, if your RAM operating system takes some process, other process will take some space. Let us say that you have 2 GB empty space. Okay. Now
Okay.
initially this 2 GB will brought into the will brought out of 8 GB, only 2 GB will be bringing into the memory, and it will keep executing. As soon as 1 GB is finishing, 1 GB is finished. Now the processor is concentrating on second GB. Now operating system, what it will do is it will empty the first GB memory, and it will bring the third GB of your file into the memory. Okay. See,
So, sir, a virtual memory is not used for execution of program. It is just for.
virtual memory is not there actually. It is stored in your hard disk. You have hard disk. You have 1 TB of hard disk. Okay, your file is stored here. Your entire file is stored here. Say 8 GB of memory. Okay, ideally you will store in hard disk only, not all the files.
Yes, sir.
You will bring the memory file into hard disk to main memory, right?
Yes, sir.
Now from main memory, it will take CPU will keep executing these instructions. Now let us assume you have only 4 GB. Say that some operating system is taking some space, say 1 GB, and 1 GB you will allocate to some other process is executing. Now you have only 2 GB left. Okay, here 1 GB left, here 1 GB left, only 2 GB is left. Okay, now what will happen? 8 GB file, instead of, you cannot fit this 8 GB in this 2 GB, right?
Yes, sir.
This is not possible. So then if this file will not bring into the main memory, your CPU will not execute.
Yes, sir.
What operating system does is, it will bring initially this first 2 GB into the main memory. Out of 8 GB file, it will bring only 2 GB into the main memory. Okay. Now your movie starts playing from 1 GB onwards initially, and it will finish. Let us assume that your CPU start executing this 1 GB of your file. Okay.
Okay, sir.
Once this 1 GB file is finishing its execution, then CPU will concentrate to the second GB. It will start executing second GB. Meanwhile, what operating system does is, this 1 GB space will be swapped. This 1 GB space will be replaced by third GB of your movie. This third GB will be brought into the memory by swapping this place. This 1 GB will go again into the hard disk. This third GB will come here. After that, after second GB, CPU will concentrate on third GB. Then this place will be replaced by fourth GB. This will be brought into the fourth space. So what is happening here? Continuously swapping. Your hard disk, from hard disk to the main memory, swapping is taking place. Continuously you are, so this file is converted into process, it is converted into pages. This address is generated by CPU pages. Your frames, CPU have limited number of frames, and you have to keep replacing it. That's what we studied. See, you have only 3 frames here, but you see the number of pages, you have more number of pages. You have only limited number of frames. This frame is main memory. Your pages are more than your number of frames. What you are doing, you are continuously replacing it. You are bringing something here, you are replacing it. Again, you are bringing something here, you are replacing it. So your system behaves as if your RAM is 8 GB, because you are playing a 8 GB movie, but you don't have 8 GB. The mechanism of how this memory management will happen is because of virtual management that is handled by operating system. So virtual memory means there is no, the memory is not literally exist, but the mechanism of how you are handling from hard disk to the main memory actually depicts the virtual memory. Does it make
Okay.
sense?
Yes, sir.
See, you have a Facebook account, right? You got Facebook account.
Yes, sir.
You behave that as a person, right?
Yes,
You
sir.
have username, but not, that is not actually a person. It's an virtual representation of yourself.
Yes, sir.
Right, so it's a mimicking. So actually virtual memory is not actually existing memory. It takes advantage of the hard disk and mechanism that is employed in a such a way that even though your file size is very large, still you'll be able to play by bringing into the virtual main memory with limited size. That is possible. The operating system takes care of it. So one of the beautiful concept of operating system is virtual memory management. This is we are discussing in with respect to operating system. Whenever you are discussing an operating system, all these operating systems will have this idea of virtual memory. Your pen drive is a hard disk, it's a storage device, it doesn't have any operating system, it
Okay,
doesn't
sir.
have any virtual memory. But your operating system has virtual memory. I mean, your operating system can able to take care of the virtual memory. Does that make sense?
Yes, sir.
That's what I discussed in the previous class, right? You did not pay attention, I guess. You see this in the previous class, virtual memory. What happens? Demand paging, you read this. Swapping, where the process reside in,
Secondary memory.
usually it's hard disk or NVM device. See, demand paging, what happens is, demand paging is one of the way where you'll execute a physical memory. Pages never accessed are thus never loaded into the physical memory. So the rest of the memory will be storing in the secondary memory. So whenever there is a demand for that page, so whenever there is a demand for a particular page, then only it's loaded. Rest of the time it will be storing in the secondary memory. So what happens, it will be keep on swapping. Suppose this bit is valid, what are the valid bits we will store in the memory, what are the invalid bits we'll keep in the backing store, that is the secondary storage. Whenever a new process is coming, that will be brought into the memory. If the frame is available, you will allocate it. If frame is not available, you will replace it. You will push that into the swap it with the existing page. So that's what we discussed in the previous class, right? So when an operating system sees that a particular page is invalid, it will go on backing store, it will allocate a free space, update the page table. That's what we discussed in the previous class. So whenever there is a page replacement algorithm, so one way to do that is FIFO. FIFO method is one way that you are replacing. You can see that the number of pages are so much, you have only 3 frames. With 3 frames only, we are able to execute this many number of pages. And we can continue to do that. But what happens is the page faults will increase. The number of page faults increases, the system will performance will decrease. Does that make sense?
Yes, sir.
Okay. Now FIFO replacement algorithm, we try to understand the number of page faults is 15. So let us now continue our discussion with other algorithms. Any other doubts? Okay. So let us now continue with optimal page replacement algorithm. So optimal page replacement algorithm, instead of replacing the first in first out, what it does is it will replace the page that will be not used for the longest time. So it will read the string, it will observe the string, and it will see that whichever the page will be not used for the longest time, that page will be replaced. So use the page replacement algorithm. So because that will be not used for the longest time, then the number of page faults will decrease. You can observe here, 7 will be initially brought into the frame, 0 will be brought into the frame, and 1 will be brought into the frame. Among 701, which is the longest period that will be not used? The 2 is coming, 0 is coming, 3 is coming, 0 is coming. So among this 0 and 1, which is longest? 701, which is the longest page that will come later? Okay, so 2 is coming, 0 is coming, so that is there. 3 is coming. So 0 is coming 1, 2, 3 times. 1 is coming, you see, here. 1 is coming here. Now 7 is coming at the end, right? You observe this string, you observe this reference string. After filling this first 3 details, when compared to 701, which is coming late, 0 is coming immediately, so we will not replace this. Next, 1 is also coming near after that. So 7 is the longest one which is coming late. So because 7 is coming late, we will replace 7 with the next element. Okay, so the next immediate frames that will be replacing. So idea is like longest period of time whichever is coming, we will replace that. So when compared, when we observe this reference string, 0 is coming immediately and 1 is coming after that. 7 is coming very late, so we will replace 7 with the next frame. So 2 is coming, 2 is not there in this frame, 2 need to be replacing any one of this page. uh, so which one should be replaced? 701. Earlier in the first come first serve, 7 will be replacing and will go to the next position. But now we will study the reference string. Whichever is coming late, we will replace. 7 is coming late and we will replace 7 by 2. So after that, 0 is coming, so no need of page fault, no need of replacement. Next 3 is coming. So 3 is not there in this frame. When compare this, which page should be replaced, we will study again the future string. So 0 is coming, 0 we will not replace. So 4 is coming, 4 is not there, ignore it. 2 is coming, so 2 will not replace. Okay. So next, only one element, the longest will come is when 1 is coming longest, right? So after 0 is coming, so 2 is coming first, so these pages we will not replace. We'll replace 1 because 1 is coming last, so 1 will be replacing by 3. Okay, next 0 is coming, so already it is there in the frame, no need of page replacement. Next 4 is coming, so 4 if I have to replace, we have to study which frame will come long from 0 to 03. So 2 is coming immediately, will not replace 2. 3 is coming immediately, will not replace 3. So the next longest will be 0. So 0 will be replaced by 4. After that 2 is there already, 3 is there already. Next 0 need to be replaced. From 0, when we need to replace it, we will study the frames again. Whichever is coming longest, we'll replace that. So 3 is coming, so we'll not replace 3. 2 is coming late, so 2 also will not replace. 4 is not there, so we can replace 4 by 0. After that, 3 is coming, no need of page replacement. 2 is coming, no need of page replacement. 1 is coming, so when 1 need to be replaced, we will study that whichever is coming long. So 2 is coming first, so we will not replace that. 0 is coming after that, we will not replace it. So compared to that, 3 is coming the longest, so 1 will be replacing 3. After that, 2 will come, will not replace it, it's already there. 0 is coming, it's already there, no need of replacement. 1 is there, it's already there, no need of replacement. 7 is there, we need to replace one element. Which one will replace? 0 is coming, will not replace that. 1 is coming, will not replace that. So 2 is not coming, 2 will be replaced by 7. So next element, 0 is coming, no need of page replacement. 1 is coming, no need of page replacement. Okay, is this make sense? By observing the
Yes, sir.
future reference strings, whichever is coming the longest, which will be not used for the longest period, that we will replace with the existing frame. So when we do that, the same example that we studied in the FIFO, the same string, this is the same string, you can observe that FIFO also we studied the same string, but with optimal page replacement we are bringing only 9 faults. Now the same algorithm, when we apply P4, we ended up with 15 page faults. Now here only 9 page faults. So this is better, right?
Yes, sir.
Anybody understood how, anybody has any doubts in how we are replacing the page? Anybody want me to repeat this? Optimal page replacement observes that by observing the future string, whichever is not coming for the longest time, that page will replace. So after filling 701, 2 page we need to load into the frame, but 2 is not there in the frame. We need to replace some page. So which page should be replaced? For that, we will observe the string. Whichever is coming longest, that page will replace. Means whichever is coming near, we will not replace it. So after this 2, when we observe, 0 is coming first, followed by 1 is coming. After that, 7 is the longest. So 7 will replace it. After filling this, we will keep studying that whether the page replacement is needed or not. 0 is there, no need of page replacement. Next 3 is there, but 3 is not in the frame. We need to replace some page by 3. By observing, studying this string, 0 is coming next, so we will not replace it. 2 is coming after that, so we will not replace that also. 1 is coming very long. So because 2 0 is coming immediately, we will replace 1 by 3. After that 0 is coming, no need of page replacement. When we are replacing 4, some page should be replaced from this frame. When you study this, 2 is coming and 3 is coming, followed by 0. So 2 3 will be kept in the frames. 0 will be replaced because this is the longest, so 0 will be replaced by 4. After bringing, 2 is there, 3 is there, so we are decreasing the page fault. Now 0 is need to come, which is not there, so we will study the string again. So 3 is coming again next, so we'll not replace it. 2 is coming immediately, so we'll also not replace it. So 4 is not there, we'll replace 4 by 0. Next 3 will be kept, no need of page fault. 2 is kept, no need of page fault. 1 is coming, 1 is not there in the frame, we need to replace some page. So by studying this, 2 is coming and 0 is coming, so 3 is the longest, so 3 should be replaced by 1. After this, 2 is coming, no need of page replacement. 0 is coming, no need of page replacement, that is no need of page fault. 1 is coming, no need of page fault. 7 is coming. By studying the 0 and 1 is coming next, so 2 is not coming, we will replace 2 by 7, hence no need of page replacement. By studying the string, what comes ahead, we will decide the optimal page replacement algorithm, and we encountered that by doing so, we will be able to achieve only 9 faults, 9 page faults. So 1 2 3 4 5 6 7 8 9, you see that. So in FIFO we got 15, but in optimal page we got only 9. So this is better. Okay, this is better than FIFO. Now what is the problem with this algorithm?
Sir, we have to compare all the elements of this frame.
Okay, any other disadvantage?
Sir, we might not know the order of the reference string
Right. So in
beforehand.
order to apply the optimal page replacement, you need to have a knowledge of upcoming pages. In order to make the optimal page replacement, you need to have a knowledge of all the page faults that is coming ahead in the future. We don't know that. Okay, next page will be 1 7 2 3 4 5 6. We don't know. We don't have the future knowledge of these pages. Which page will come next? Unless you have that information, you cannot implement optimal page replacement. In order to execute this optimal page replacement, in order to find which will be not used for the longest period of time, we need to have this information. But which page will come next, we don't know. Which page will be demanded, we don't know. So when we don't know, we cannot implement this practically. But why we are studying? Because this is the best algorithm. Whenever somebody is proposing an page replacement algorithm, when we compare this optimal page replacement, this is the best algorithm theoretically, but practically it is not possible. Okay, so hence for theoretical comparison, whenever somebody is implementing some other approach, to compare how best your algorithm is close enough to the optimal page replacement, then that could be the best algorithm. So optimal page replacement is not practical because unfortunately it is difficult to implement because it requires a future knowledge of the reference string. But we encountered a similar, if you observe that CPU scheduling, shortest job first. If you know whichever the job is shortest, if you schedule it first, then the waiting time will decrease. That we studied in CPU scheduling, right? You remember? First come, first serve, shortest job
Yes,
first.
sir.
What is the problem with shortest job? We don't know which job process will take less amount of time. That knowledge we don't have. How much process will take to burst itself? We don't have that information with us. The same way, but uh, in the same way, optimal page replacement also requires future knowledge. But why we still studied SJF? Because this is the best algorithm which will decrease the shortest time, shortest waiting time. Compared to other algorithms, for comparison, how best is your algorithm, we will study the SJF. Likewise, optimal page replacement. Also, in page replacement algorithm, this is the best one. To compare that, for mainly optimal algorithms, you use it for mainly for comparison studies. For example, it may be useful that a new algorithm, which is not optimal, but if it is within the percentage of 12.3% of optimal at worst and within 4.7% on average, then that is a good algorithm. A new algorithm which falls within this category, 12%, 12.3% of optimal at worst and 4.7 on average, still that is good enough, right? So for comparison purpose, we will study the optimal page replacement algorithm. Does this make sense?
Yes, sir.
Okay. Now let us continue another algorithm, that is LRU page replacement. LRU page replacement is least recently used algorithm. So instead of having future, we will look in the past. So FIFO algorithm uses the time when a page was brought into the memory. Uh, But whereas optimum algorithm uses the time when the page is to be used, means it looks into the future. But when we look into the past, if we use the recent past of an approximation of the near future, then we can replace the page that has been not used for the longest period of time. So which means whichever recently used, that we will, when a page must be replaced, we will, LRE chooses the page that has not been used for the longest period of time, um, from the past information. Okay, so this is like optimal page replacement algorithm looking backward in time rather than forward. Okay, so we can think of this strategy. Optimal page replacement will look forward, but least recently used will look in backward. Let us take one example. The same string we will try to observe with this example. Okay, so initially LR uses the least recently used among this 701. Among this 701, which is least recently used? 7, right?
7.
So 7 will be replaced by 2. Okay, so after that 0 will come. 0 is there already in the frame. Now 3 will come. Among these 3, which is recently used? 1, right?
1.
Because 2 is used here, least recently used. When you compare backwards, when we compare the backward, 0 is used just now, 2 is used before that, but 1 used least recently used, 1 is the least recently used. So 3 will come in place of 1. 1 will be replaced by 3. Okay, now when you come to this position, when you come to this position, 3 is least recently used, 0 is before that. When 0 is coming, 0 is already there, no need of replacement. When 4 is coming, which is not in this frames, which one will be replaced?
2.
2, because that is the least recently used. 0 is used just now, 3 is used before that. So 2 is the least recently used, so that will be replacing 4. So 2 will be replaced by 4. So when you compare this string, 4 will be recently used. Before that, 0 is used recently before 4. Now 3 is the least recently used. When a new string is coming, that 2 will be replacing the least recently used, that is 3. So 2 will be replacing 3. So when a new string is coming 3, which is not in the frame, we will see again backwards, which is the least recently used. 2 is least recently used, 4 is least recently used. After that, the most least recently used is 0. So 0 will be replacing 3. You read this again. uh, 3 is recently used, 2 is also least recently used, 4 is the least recently used. So 0 will be replaced by 4. It looks from the backwards direction. Okay, next 3 will come. 3 is already there, no need of page fault. 2 will come, 2 is also already there in the page, in the frame, no need of page fault. 1 is coming, so which is recently used? 2 is recently used, 3 is recently used, 0 is the least recently used, so 1 will replacing 0. Okay, after that 2 will come, 2 is already there, 0 will come, which is recently used? 2 is recently used, 1 is recently used, so 0 will replacing 3. Okay, 0 will come in place of 3. Next 1 will come, 1 is already there in the page, and 7 will come. So which is recently used? 1 is recently used, 0 is recently used, so 2 is the least recently used. So 2 will be replaced by 7. After that 0 will come and 1 will come. You see this? And how many page falls in this case? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 page falls, right? So 12 falls. So compared to FIFO, in FIFO we got 15.
15.
In optimal,
9.
9. But in least recently used, we got 12. It is better than FIFO, but not as good as optimal. But this we can implement it because it is based on the past information. Okay, least recently used is because of past information that we have. We can see that which is recently used, and we can replace that with the uh, available frames. Because of the past history, we can easily implement the LRU page replacement algorithm. Does this make sense?
Yes, sir.
Okay. So LRE policy is often as good as page replacement algorithm, and it is considered to be good. The major problem is how to implement the LRE replacement. Okay. When it comes to implementation, we need to keep an extra information, right? What is the elements, pages that are coming again and again? We need to track this information. We need to have this information to store somewhere to verify that which is the least recently used. So we need to, when implementation comes, we need some extra effort. Okay, so LRE page replacement algorithm may require substantial hardware assistance. So the problem is to determine an order of the frames defined by the time of last use. So two ways you can implement this. One is you can keep a counter, or you can keep a stack. Okay, two ways. You keep counter, how many times 7 repeated, how many times 0 repeated, how many times 1 repeated, how many times 2 repeated. You keep a counter, because based on the counter you can able to easily calculate, right? If you keep a counter, so how many 7 came, you keep a counter in an array. 7 came, repeated, came one time. 0 came, this came one time. 1 came, this is one time. 2 came, which is recently used, among this is 7. So 7 will be replacing by 2. 2 came one time. 0 came again, this came 2 times. Okay, then 3 came, 3 will be replacing, which is the least recently used. 3 will be replacing 1, and 0 will come again, this will become 3 times. So 0 will not replace it. You see, observe this, 0 will not replace it. Okay, you can keep a counter like this, whichever is coming, counter 1, counter 2, counter 3, like that. You can keep a counter and see that based on this counter, whichever is coming late, we can observe that, right? Based on the counters, you can implement this. Or else you can keep a stack. There are two ways of implementation. Now, let us counter is very easy. You can keep counting the number of elements which occurred in the past. That will help you to determine which will come, which need to be replaced. Whichever the counter is less, you replace that page. But whereas stack is bit tricky, we will understand how to implement LRU, least recently used page replacement algorithm using stack. So like optimal replacement, LRU will not suffer with any Bellides anomaly. Bellides anomaly is when you're increasing the page fault, when you are increasing the frames, your page fault will not increase. It will substantially decrease. It will not suffer. But it needs an extra effort of taking care of stack. For example, this is your reference string. So in stack, you push then element 4, you maintain a stack 4, uh, push into the stack, 7 is coming, then push again, 0 is coming, push, 7 is coming. Whenever an element that is coming newly, you will implement, you will bring that into uh, top. Okay, you'll whenever a new element is coming, we'll bring that into top. Okay, for example, let us see that how that is working. uh, okay, so initially now stack is 4 and 7 and 0. uh, Whenever you are bringing a stack, that should be on the top. So whichever the element that is least recently used, that you can keep that as a uh, in the stack. Okay, what happens, we will maintain a stack. Okay, so initially 4 will come, you push into that element, 7 will come, you push again, 0 will come, you push into this element again. So whenever is 7 is coming, 7 already in the frame, correct? 7 already in the frame, so we will not worry about that. We will not worry and we will continue which is already there. Okay, so there is no problem. So 1 will come, 1 will be stored, and 0 will come. Again, 0 is already there in the stack. Again, 1 will come, 1 is already there. 2 will come, let us say that 2 is there, we are storing this stack. Next, again 1 will come. So this order is changing, right? Why this order is changing? Because let me do this one more. Whichever is least recently used, we will bring that into we will bring that element into the top. Now we are pushing this element. 4 is pushed into the stack, 7 is pushed into the stack. Now 0 is pushed into the stack. Now 7 is coming, so 7 is the least recently used, so your stack should change to 4, 0, 7, because 7 is the least recently used, that is brought again top of the stack. Next 1 is coming, so 1 will be 4, 0, 7. 1 is the least recently used. Again 0 will come, 0 is the least recently used, then 0 will be on the top, but 0 is here already, so this should be brought into the top of the stack. So what will happen to your stack now? 4, 7, 1 and 0. So whichever you are using recently, that you are bringing into the top. Now after 0, next element is 1, so again 1 you are bringing into the top of the stack. What will happen? 4, 7, 0 and 1. This is the least recently used. Next element 2 is coming, so you are adding one more element here on the 2. After 2, your 1 is the least recently used, so this stack will change again. 1 is the least recently used, right? So 4, 7, 0, 2, and 1 is the least recently used. Then again 2 is the least recently used. Again 2 is brought into the top of the stack. When you're bringing 2 again top of the stack, what will happen? So 4 will be here, and 7, 0. So 2 you're bringing here. So 2 should come on the top. 1, 2. Okay. This is 2. Then you are bringing 7. So when you're bringing 7, 7 should be on the top of the stack. So 7 should come on the top. This will change to, sorry, I'll write here. Okay. So 7 should be 4. 4 will come, next 0, next 1, next 2, next 7. Okay. After that 1 will come, then 1 should be brought again on the top of the stack, which should come 4, 0, 2, 7, 1. Next 2 will come, so 2 will be brought again at the top of the stack. So 4, 0, 7, 1, and 0. Okay, so you are maintaining the stack like this. Is this make sense?
Yes, sir.
How we constructed the stack? So whenever an element comes, you will bring to the top of that element, top of the stack. So when you are maintaining a stack, you will understand which is the frequently coming element. So the frequently element which is on the coming will be on the top. So whichever in the bottom, that is the least recently used. Is that correct? Among this, 0 is the recently used. After that, 1 is, you study this. Sorry, this should be 2, right? This should be 2. After 1, 2. You see this 2, when you reached here, 2 is the recently used. Next 1 is the before recently used. After that, before 7 is the recently used. Next you see that again 2 is there, 1 is there, 2 is there, 1 is there, 0 is the next recently used, and 1 is the again 1 is there, 7 is there, and you see that 4, when you compare this, 4 is the last recently used. Okay, when you're maintaining a stack, your top says that that is the recently used, don't disturb that. So you are keep counting whenever an element is coming, you are bringing on the top of the stack, which says that the bottom of the stack is what the least recently used. Whenever you are trying to replace it, you replace the bottom of the stack. Whatever the element that is on the bottom of the stack, that element can be replaced. Does that make sense?
Yes, sir.
So let us apply this idea here for this LRU replacement. So let us maintain a stack. So initially, what is the element you pushed? 7. You push element to 0. You push element to 1. Now again 2 is coming. When 2 need to be coming, which is the least recently used? 1, 0 is the least recently used. So the element what you will replace is with bottom of the stack. So 7 should be replaced by 2. So 7 is replacing by 2. So when you do that, 7 will go away. Then your stack is updated 0, 1, and the least recently used element is 2. Okay. You can keep this stack if you're having size, but you can decide, or you can push on the top of the element. That's also fine. Okay. So this will be your stack now, new stack. So among next element is after 2 zeros coming. So your stack will be updated, 1 will be pushed down, 2 will be again, then 0 is the least recently used. Next 3 will come. When 3 is coming, which element will be replaced? This bottom element will be replaced by, wherever 1 is there, you replace that element by 3. Okay, so your stack will update to 2, 0, and least recently used this element is 3. Next 0 is coming, so your stack will update by 2, 3, 0, because the 0 is coming here and it will update. Okay, now 4 is coming, 4 is not there here. Which one you will replace? You replace 2. 4 will be replaced by 2, so your stack will update again. 3, 0, least recently used is 4. Next element 2 is coming, so 2 is not there. 2 will be replacing which element? Third element, right? This is the bottom of the stack. So wherever 3 is there, 3 will be replaced by 2. You can see this 3 is replacing 2. Okay, now your stack will update to 0, 4, and 2. Next element is 3. 3 will be replacing the least recently used is bottom of the stack, that is 0. 3 will be replacing 0. You see this 3 is replacing 0 because that is the least recently used. So your stack will update to 4, 2, and 3. Okay, next element is 0 is coming. 0 is not there, so 0 will replace bottom of the element, that is 4. Okay, 0 is replacing 4, so your stack will update to 2, 3, and 0. Next element 3 is coming, so 3 is already there in the stack, so we'll update 3, uh, 2, so 0 will be pushed down, 3 will be brought into the top. Next 2 will be the next element, so 2 will be brought again into the stack. 0, 3, 2. Next 1 is coming, 1 will be replaced by bottom of the element 0. You see this 1 is replacing at the 0th position, so 1 will be coming, then your stack will update to 3, 2, 1. Okay, next 2 is coming, so 2 is already there, so 3, 1, 2. Your stack is updated. 0 is coming, 0 will replace 3. Wherever 3 is there, you see that 0 is replaced at the third page. So your stack will update again to 1, 2, 0. Next 1 will come, your stack will update to 2, 0, 1. Next 7 will come, 7 will replace 2. You can see that 2 is replaced by 7. So your stack will update to 0, 1, 7. Next 0 will come, so your stack will update to 1, 7, 0. Next 1 is coming, so 1 will be brought to the top. 1, 0, 7. So now suppose let us say that 2 is coming. Which one will be replacing when this what will be the next page? When 2 is the next string, what will be the next page? Here when 2 is coming, which one it will be replacing?
So 7.
Yes, because bottom of the stack is 7, so it will be replacing your new frame will look like 1, 0, 2. Okay, does this make sense?
Yes, sir.
So maintaining a stack will help you to implement LRU page replacement algorithm. So when we are doing this, when you increase the number of pages, when you are increasing the number of frames, we will obviously decrease the number of page faults. Okay, so with this is the 3, right? So let us now discuss, let us now apply this idea with 4 frames. Can you tell me with respect to 4 frames? You take this with 4 frames. Apply this algorithm with 4 frames. Tell me how many page faults are coming.
So
Apply
2107.
LRU with 4 frames. How many page faults will come? You'll apply here 7, 0, 1, 2. This will take 4 page faults. Next element will be 0. It's already there. No need of bringing. 3 will be coming. Which one you will replace? Up to this we finished. 0 is already there. We finished. Next element is
7.
3. When 3 is coming, which one you will replace?
7.
7 is the least recently used. Okay. We will replace 7, 3, 0, 1, 2. Okay, so we replace 3. Next 0 is coming, which is already there. 4 is coming, which one you'll replace? 3 is recently used, 0 is recently
1.
used, 2 is recently used, so 1 you'll replace. So your page number of page replacement will be 1 you'll replace. So 3, 0, 4, and 2. So next is 2, it's already there. 3 is already there. 0 is already there. Again 3 is already there. 2 is already there. 1 need to be replaced. Which one you will replace now? 2, 3, 0.
4.
4 will be replaced. Okay. 3, 0, 1, 2. Okay, so 1 will be there. So 2 is already there in the stack, sorry, in the frame. 0 is already there. Again 1 is already there. Now 7 is coming. 7 will be replaced by
3.
3. Okay, 7, 0, 1. Okay, now 7 is done. 0 is there. 1 is there. So how many page faults we encountered? 4, 5, 6, 7, 8. 8 page fault. Right. Up to this is 4. This is 5. This is 6. This is 7. This is 8. So when the number of frames increasing, we are decreasing the page fault. This is 8. Sorry, 8 faults. Okay. So when the number of frames increased to 4, the page faults decreased from 12 to 8. When 3 to 4 it is increasing, the number of page faults is decreasing from 12 to 8. So when you're increasing the number of frames, your page faults is not increasing. So we can say that optimal LRU does not suffer from Belady's anomaly. You can verify this with five frames also. Okay, you can verify this 5 frames and cross check. So does that make sense what I'm saying?
Yes, sir.
Okay, so we will take 5 minutes break, 5-10 minutes. It's 4 o'clock. We'll get back again at 4:10. We'll discuss few things, then I'll stop. Okay. So let us take break for 5-10 minutes. Meanwhile, you can verify with 5 frames and 6 frames and see that how many page faults are coming. If you are having time, if you want to work, you can tell me with 5 frames how many page faults, with 6 frames how many page faults. You can verify with 3 frames you got 12 page faults, with 4 frames you got 8 page faults. Increase the number of frames and check whether your page faults are decreasing or not. So meanwhile, we'll take a break for 10 minutes. We'll get back after 10 minutes. Okay, guys, shall we restart?
Yes.
Okay, so let us continue our discussion on page replacement algorithms. So we can observe that how many page faults come with 5 and 6 frames.
Sir, with 5 it is 7 and with 6 it is 6.
Okay, so it is decreasing. That's good. So when the number of frames are increasing, it is number of page faults are not increasing. So that's better. So what happens is like so we can exhibit that it does not suffer from Belides anomaly. Okay, they can never exhibit Belides anomaly. Okay, so counting based page replacement also is another page replacement algorithm. There are many algorithms that can be used for page replacement. So we can keep a counter of the number of references we have been made to each page, develop the following two schemes. So there is other two schemes that will come under counting based page replacement, that is least frequently used or most frequently used. In least frequently used, uh, the page will the smallest count can be replaced. Most frequently used, the smallest count was probably just brought in and is yet to be used. So most frequently used uh, will be used. So there these are two approaches. So we can expect that neither most frequently used or uh, least frequently used replacement is uh, common, because the implementation of these algorithms is a bit expensive. They do not approximate the optimal replacement well. So there are other these two approaches, but that's the problem. So we will discuss thrashing, and I will stop. After discussing thrashing, we'll discuss about your quiz and in some exam and practical exams, and we'll stop. What happens is, what is thrashing we will learn, then we will continue our discussion. Okay, so consider what occurs if a process do not have enough frames. uh, that is the number of frames, the minimum number of frames it needs to support pages in the working set. What happens is, when there are no enough frames and you have more number of pages, what will happen is quickly page fault will happen. Okay, uh, if a process does not have enough frames, obviously, right? So you have only, you can observe that with you have only 3 frames here, you don't have enough frames, and number of pages are there, quickly page fault will happen. But whereas in 4 and 8, the page faults are less, because when the frames are more, the page faults will not happen quickly. Okay, so when page faults are increase, when frames are increasing, page faults are decreasing, because when you don't have sufficient number of frames, when you don't have enough frames, quickly page fault will happen, because the you don't have minimum number of frames that needs to support the pages in the working set. So at this point, whenever the page fault happens, we will replace the page. Since all these pages are active use, it must replace a page that will be needed again right away. Suppose in this case, we will see here. Suppose in this case, uh, here, if you read this string, in this case, 3 will be replaced immediately, and let me tell you one more example that will make sense. 0 1 0. Okay, fine. So we can 3 2 1 2. Okay, so you can see here one example. Here we are replacing 0, right? Here we are replacing 0, and page fault happened, 1 happened. Then again this 1 is replacing, 1 will be continuing, and again we are bringing 0, replacing 3. Let me put this in a proper way. 0 is a page fault. We replaced with 1. Okay, page 0 is replaced by page 0 is coming. That page is replaced by 1. But after some time, page 0 is coming again. This is replacing 3. Does this make sense what I'm saying? I repeat it. Page 0 is there in the frames. This is swapped with page 1. Then after some time, this page 0 is brought it again into the frame within short period of time. You see this is a short period of time. 0 is there, but again it is replacing 3. So that's what I meant to say here. So whenever all pages are active, whenever it is replacing a page, that may be needed right away again. Again, it may be needed right away. What happens when such things happens? Page quickly falls again and again and again, replacing pages that will bring back immediately. Okay, so that will bring back immediately. For example, we can take 2, 0, 1. With this 3 page faults, we will do that. Okay, let us say that 2, 0, 1. Now we had to suppose 3 is coming. Which one you will replace?
2.
3, 0, 1. Again 2 is coming. Which one you will replace?
0.
Again 0 is coming. Now which one you will replace?
1.
3, 2, 1. Right. Now again 1 is, 1 will be replaced by 0. 1 will be replaced by 0. Now 1 is coming. Which one will replace?
3.
Now 3 is coming again. Which one will replace?
2.
You see what is happening here?
Yes, sir.
For the pages are same. 201, 2013 is same. But because it's active pages, you are creating page faults every time because they are needed right away. Okay, so whenever such things happens, page faults will happen again and again, replacing the pages that will bring back in immediately. This is the bad way of doing. Even you do least recently used also, still you are making the page faults. So the high paging activity is called thrashing. Okay, the high page activity, when you are making page faults more number of times, this is called thrashing. So a process is thrashing if it is spending more time paging than executing. You need to execute this process pages. CPU will execute this whatever it is in the main memory. The frames, right? These are frames. This frames represents in main memory. Whatever the contents are here, it need to be executed. But every time now main memory asks, CPU asks, I need a page 0, which is not there. You will do a page fault. You will bring it back again to the main memory from hard disk. Then it will execute. Now CPU tells that I need page 1. Then again you go and bring back from the secondary memory. What happens? Till the paging, replacing will happen from main memory to secondary memory. The replacement will happen. The paging will happen. CPU will sit idle. CPU will not execute because that page is not there. So if frequent page fault happens, the process will spend more time in paging than executing. Okay. So when such scenario happens, we call that as a system is going in thrashing. So thrashing results in severe performance problems. Okay, so you can expect that because the processor is not utilized properly, operating system is working on paging, that page is not there to finish the process, so CPU will sit ideally. So the thrashing will result in severe performance. Let me produce space. Okay, so what happens is the operating system monitors the CPU utilization. If CPU utilization is low, we need to increase the degree of multiprogramming, right? Ideally, the processor is not utilized properly. What you will do, you will increase the multiprogramming. You will put 2-3 processes at a time. If CPU utilization is low, we will increase the degree of multiprogramming by introducing new process into the system. But page replacement algorithm replaces pages without regard to the process to which they belong. Now suppose the process enters a new phase in its execution, needs more frames. It starts faulting, taking frames away from the other process. This faulting process must use the paging device to swap in and swap out. Queue for using paging device will empty this. So as a result, what happens is um, the process will wait for paging device, CPU utilization will decrease. Even though the CPU scheduler sees that CPU utilization is decreasing badly, it will increase the degree of multiprogramming as a result. Does it make sense? I'll repeat again. Suppose you have a main memory, say process P1 is there, you have only secondary memory is there, hard disk. This process P1 is creating page faults. This process P1 is bringing again and again page faults. Okay, when page faults are less, CPU is not utilized properly, CPU performance will go right, because operating system is spending more time on paging, CPU will go less. When CPU performance is less, what happens is, to increase the CPU utilization, new process is introduced. Process P2 will start executing from the ready queue. Okay, process P2 will start executing from ready. Process P2 will come, then instead of two spaces, again this process P2 will come, it will be replacing process P1 page. It will come and occupy some memory space in which is already occupied by P1. Now this each process replace the other process page, which will increase more number of page faults. Does this make sense?
Yes, sir.
I repeat one more time. Pay attention. When page faults are happening frequently, the CPU performance will go low. Whenever CPU is low, what operating system thinks is that CPU is not getting enough process to work on. So operating system assigns new process. But already process P1 is suffering from page fault. Process P2 will come and it will occupy some more memory. And this will push the other process P1 page faults is happening. That will be disturbed by another process P2. Okay, so that's what I have written here. Read one by one. So operating system monitors CPU utilization. CPU utilization is low. We increase the degree of multiprogramming by introducing a new process into the system. Process P2 will come. Page replacement algorithm replaces pages without regard to the process in which they belong. Already this memory space is already occupied by P1. P2 page replacement algorithm will come and it will disturb the P1. So when a process enters a new phase in its execution, need more frames. So it start faulting, taking frames away from other processes. P2 will come and it will take the frames belongs to the P1. This faulting processes must be using paging device to swap pages in and out. They queue up the paging device till the ready queue empties. What happens is, this process will keep fighting for the frames. Again here the page fault will increase because of this paging device. Again CPU utilization will decrease. Okay, so the CPU scheduler sees decreasing in CPU utilization. Again CPU will say that let us introduce some more processes to increase the degree of multiprogramming. So another P3 will come saying that CPU is again not utilized properly. Is this scenario is making sense?
Yes, sir.
So you think that the CPU utilization is increasing as the degree of multiprogramming is increasing. Uh, so CPU need to be utilized properly. So you are having only one program, your CPU is utilized this much. you have only one programming, your CPU is utilized this much. When you have two programs, your CPU utilization is increasing. When you're having three programs, again your CPU utilization is increasing. When you keep on increasing up to certain point, it will, the degree of multi-programming, when you're increasing, CPU utilization works well. Maybe up to maybe 10 programs you are executing, and this 10 programs CPU performance well. When after this, at this point of time, maybe 10 processes are in the memory, but all 10 processes is not completely in the memory. Some part of the program is in the main memory, some part of program is in the secondary memory. What happens? Keep on page faults will happen because your each process is allocated limited number of frames. They will keep happening the page faults. Whenever page faults are happening, CPU utilization will decrease. Because you are increasing the CPU utilization, you will increase the degree of multi-programming, which will further decrease the CPU utilization. You will increase the CPU, degree of multi-programming, further the CPU utilization will be decreased and it will become zero. Such kind of scenario is called thrashing. The degree of multi-programming is of course used for CPU utilization, but after certain period of time, your degree of multi-programming, even though it is increasing, but your CPU utilization is decreasing, we will call that a concept called thrashing. Is this clear?
Yes, sir.
Okay, so that's what we have written here. So new process tries to get started by taking the frames from the running process, causes more page faults, longer queue for the paging device. As a result, CPU utilization drops even further. CPU scheduler tries to increase the degree of multi-programming even more. Thrashing has occurred, system throughput plunges, page fault increases tremendously, effective memory access time increases, no work is getting done because of the process spending all time in paging. So such scenario is called thrashing. So we should avoid thrashing. Whenever such scenario happens, we should be very careful. We should decrease the degree of multi-programming rather than increasing. Okay, we should not increase the degree of multi-programming. When thrashing happens, we should decrease the degree of multi-programming. Okay, is this clear?
Yes, sir.
Okay, so as the degree of multi-programming increases, CPU utilization also increases, but all the more slowly until a maximum is reached. If degree of multi-program is increasing further, thrashing sets in, CPU utilization drops sharply. At this point, increasing CPU utilization stop thrashing. We must decrease the degree of multi-programming. We should go backwards. We should decrease the degree of multi-programming instead of increasing. So to increase the CPU utilization, we should stop thrashing. If you have to stop thrashing, we should decrease the degree of multi-program. Okay, this is one of the important concept in when we are discussing about virtual memory. This will happen. Okay, so we'll stop here. So this is all we need to learn about virtual memory management. Okay, if you have any doubts, you can ask. Okay, no doubts. Okay, I'll upload the slide in your Teams. Check that whether you'll be able to see the slides or not. Can you able to see lecture 25, virtual memory management part 2? Lecture 25, virtual memory management part 2.
Yes, sir.
Okay, go through the slides, and if you have any doubts, you can ask me in the next class. Having said that, let me give the assignment 5. So you have to implement in assignment 5 two approaches. Implement memory allocation strategies. We discussed memory allocation strategies like best fit. Through three strategies we discussed, right? Best fit, first fit, and worst fit. Implement this uh, approaches in any language as you like. Second is you implement this uh, page replacement algorithm. Okay, second is implement page replacement algorithms. You don't need to implement everything. You need to implement only three. Which are they? That is before page replacement algorithm, optimal replacement algorithm, optimal page replacement algorithm, least recently used page replacement algorithm. We can implement these three. These three are enough. Okay, your deadline is by next Thursday, 17. Okay. So can you see this assignment 5?
Not yet, sir.
Okay, it's
So
assigned.
now it is out.
Okay, see that what you are able to read.
Sir, it have two question of memory allocation and page replacement algorithm.
Okay, so you have to implement these two strategies: best fit, first fit, worst fit, and page replacement algorithms. Only three. Okay. So having said this, next Tuesday we will discuss storage management. So we finished memory management. Now we'll discuss the storage management. After that, next Thursday we'll take two more quizzes. So we conducted so far three quizzes. We have to conduct two more quizzes. So we will conduct those two quiz by next Thursday. So next Thursday 17. On next Thursday I'll conduct two quizzes. So whatever the syllabus that we'll cover till next Tuesday, that is 15th February, till that point the syllabus will be there for your 17th quiz exam. Those will be two quizzes. After that, from February 21 to 25, you will have practical exams as per your lab scheduled. So those practical exams we will conduct, followed by you will have NSEM exam. So that notification will come soon. Okay. So your schedule is already released to you.
Yes, sir.
NSEM exam schedule came already to you, all right?
Mm. No, sir,
Yes, sir.
actually, it
It
is
was
not.
given in that calendar only.
Which day, which exam is informed to you?
No, sir, actually, we didn't get that information right now.
Okay, soon you will get. So that exams will be scheduled from February 28 to March 1st week. So you have four sections. Each section will have Viva on each day on a different day. So we will conduct that. So next Tuesday will be mostly your last class for this course. So you ask your friends to come and take their exam on next Thursday, followed by practical exam, followed by NSEM exam. Okay. So
Yes, sir, okay.
next Tuesday we'll discuss storage management.
Yes, sir. Thank you.
All right. If you have any doubts so far, you can ask. If you don't have any doubts, then we will stop here. We will continue next Tuesday.